So let us hear Lucas Böltz on the verification and correctness of subgraph construction algorithm.
Yeah, thanks for introducing me and welcome to my talk. I'll start with some applications of these connected graphs without intersection. They arise in the domain of wireless networks and contain routing, boundary detection, distributed data storage. The question is now, how can such an intersection-free graph be constructed from a given graph such that the connectivity is preserved, because only removing edges would be simple. And for this, we proved in one of our former work that an algorithm for constructing such an intersection-free and connected graph is correct. And the goal is to check the steps of this proof with a theorem proof. Now I'm going to explain the algorithm we analyze in this work. It's called connected planarization, or short CP algorithm. As input, we have a finite connected graph, and we begin with an empty result set and a complete working set, and until we have edges in the working set, we proceed this if condition of the algorithm. In the end, we want to obtain a connected graph with the same vertex set but a subset of edges. So how is that algorithm working? We choose an edge in the working set, regard the intersecting edges, and if this condition is satisfied, that either u or v is connected to both end vertices of the intersecting edge, then we can add this edge to the set F and remove the intersecting links from the working set. In the next step, we have here an edge which is intersecting multiple edges. The condition is satisfied for all intersections. Therefore, we add this edge to F and remove all intersecting edges. Also, most of the blue edges are not intersecting any edge, so we could simply add them. But not all of the blue edges are added to the algorithm. As you see here, this edge ST is removed because the edge YZ is kept. In the end, we obtain this graph, which is connected and all intersections are removed. So what do we know about the algorithm? Termination and that G prime is intersection free is quite easy to see. So our focus is on showing that G prime is connected. This is not always the case, as the following example shows. If you choose the edge uv, it would not satisfy the condition to add the edge to F, therefore you remove it and the graph gets disconnected. In order to avoid this situation, we introduce a property which we call the redundancy property, and this is defined in the following way. For a pair of intersecting edges uv and wx, at least one of the vertices has to be connected to the other three ones, and you see here the four situations which satisfy this property. But this is still not enough to guarantee that G prime is connected, as the following example shows. If you choose the edges in orange and remove the intersecting edges, the vertex in the middle gets isolated and the graph gets disconnected. And to avoid this situation, we introduce a further property, the so-called coexistence property, which is defined for a triangle of three vertices, uv, vw, and vu, and for a vertex x located in the interior of this triangle, this vertex s has to be connected to u, v, and w. And the redundancy and coexistence property together, if this is satisfied for every intersection, every triangle in a graph, we call such a graph a redundancy and coexistence graph. Therefore, in the input, we require this graph to have the redundancy and coexistence property, and in our former work, we show that a G prime is connected in this case, and in this work, we're going to verify the main steps in this proof with the theorem proof for set 3. So what do we need to do this? We have to reason about geometric graphs. In the first step, we have to express conditions in Euclidean plane geometry, such as that uv and wx are intersecting and that x is in the interior of a triangle. Then we have to model the graph properties, first for the input and then also for the output graph. In the last step, we have to reason about the connectivity. Now to the modeling of the Euclidean plane geometry. We used an axiomatization related to a fragment of Hilbert's axiom system and started with an axiom left, which has the initial meaning that this point W is left of a line passing through U and V, and in this case W1, W2 and W3 would be left of UV, while W3, W4 and W5 would be left of VU, and the point which is located between them is both left of UV and left of VU. We needed 6 axioms to define a predicate left which satisfies these properties, and based on this predicate we defined the predicates for intersection and inside. We call these axioms, which fall in the Bernet-Schönfinkel class, axioms for geometry, and if we can derive some formula phi from these axioms of geometry, then phi holds in the Euclidean plane geometry, but the converse is not necessarily true because we only model part of Hilbert's axiom system. Afterwards, we defined the properties for the input graph. Here these 3 properties are required: that no self-loops are allowed, that edges are symmetric, and that edges exist only between vertices. And using the predicates for intersection and inside, we can define this redundancy and coexistence property, which we required as a property for the input graph. And then let's have a look at the properties for the output graph. This edge set is also symmetric. It's a subset of the edges of the input graph, and no intersections occur in this set F. And furthermore, the edges in F has to satisfy the CP condition, which means for every intersecting edge, either U or V has to be connected to both end vertices of the intersecting edge. And this example here shows that UV is not satisfying these conditions, but all the other edges are satisfying this condition. And in order to prove the correctness of the algorithm, we need to define a predicate for deleting edges which remove other edges. This predicate is true if U1 is deleted by an intersecting edge Wx and the redundancy edges Wu and Wv exist for this intersection. An edge can be deleted for 2 reasons: either if the CP condition is not satisfied or if an intersecting edge was added to F before. Here's an example where the edge Uy is deleted by the edge Wx. And in total we have 41 axioms so far defined: the axioms for geometry, the axioms for graph, and this redundancy and coexistence property, which we use as input for all the proof steps. So now to the idea of the correctness proof. We assume for contradiction that the resulting graph is disconnected, but we know the initial graph was connected and there were edges connecting this blue component X with vertices outside this component. And our goal is now to find a path connecting the component as X and Y. The proof is done following the 3 lemmas. We first show that an edge that is not in F is intersected by an edge in F. Then we show that there exists an edge in E connecting these 2 components where all intersecting edges in F are in Y. And in the last step we show that there exists a path connecting the 2 components on the finest path of a convex hull formed by edges in F. So now to the proof of the first lemma. This is done in 2 parts. We first show that there exists a sequence of edges in E intersecting with U1, V1. The first step we consider a sequence with 2 edges. In the second step a sequence with 3 edges. In the second part we show that such a sequence cannot be cycled by distinguish multiple subcases where all possible situations are checked. So this is the situation of the first step. We have an edge U1, V1, which is deleted by an edge W1, X1, and this edge W1, X1 is again deleted by an edge W2, X2, and then we show that one of the edges W1, W2 or W2, XY is intersecting with U1, V1. And in the first case that W2, X1 is the intersecting edge, this is also deleting U1, V1. And yeah, therefore we see that there is at least one other intersecting edges. And what is important to note here, without a coexistence property, a counterexample would be found in this case. And then we continue for a larger sequence of edges. So if this edge W1, W2 is deleted again by another edge W3, X3, then we see there are still another edges which intersect with U1, V1. In this case, it would be W2, W3, and the step 2b where X2 is and W1 is the edge intersecting with U1, V1 is analogous. Yeah, and after we know that there exists such a sequence, we are going to show that a cyclic sequence, which would be this case, that after the sixth edge, x1, w3, the next edge of the sequence would be again w1, x1, is not possible. We would use it to this counterexample of size 2, where the sequence would contain only the edges w1, x1 and w1, w2, respectively w1, x1 and wx2. And as you see here, we would have an intersection of edges where the redundancy property is not satisfied. So this cannot occur, and therefore this sequence has to come to an end, and there's at the end of the sequence an edge which has to be in F. Now we are looking at the edges connecting the components x and y. In the first step, we have this edge u1, v1, which is deleted by an edge w1, x1 in F, and then this edge v1, w1 is deleted by another edge w2, x2 in F, and we see that either w2 or x2 is inside this triangle u1, v1, w1, or w2, x2 is also deleting u1, v1. And the step 8b shows that a cyclic sequence can also not occur here. And with this, we see that there exists a sequence of edges connecting x and y, and we prove that this sequence is not cyclic. Therefore, at the end of the sequence, in this case it would be v1, u4, there's an edge where all remaining intersecting edges in F are in component y. Now some words about the automated reasoning which we used in the proofs for these first two lemmas. All axioms are universally quantified and do not contain function symbols, therefore they fall in the Bernet-Schoenfinkel class. Satisfiability of formula in this Bernet-Schoenfinkel class is decidable, and set 3 can decide this Bernet-Schoenfinkel class. In the last step of the proof, we regard an edge u1, v1, where all intersecting edges in F are in component y. We choose the one with intersection point q closest to the component x, and then we show that at this finest path of the convex hull connecting u1 with w1, all edges on this path are not intersected by edges in F, and therefore by lemma 1 we know that all these edges of this path along the convex hull have to be in F, and therefore they the edges of this path connect the components x and y, which leads in the end to a connected graph. So how did we model these convex hulls in the interior of a triangle? We again used some predicates with I1 and next of I1 is not null. Then, for example, next of I has to be inside the triangle of I, xi, and wi, and I has to be inside a triangle formed by u1, v1, and next of I, and w1 has to be left of the line passing through I and next I, and this is a decidable fragment of the theory of pointers where we refer to a paper of Nikula and McPeak. So now I'll come to the conclusion of my talk. The main steps of a correctness proof for a subgraph construction algorithm were verified using the theorem proof for set 3, and as future work we plan to find a simpler approach to prove the correctness of the algorithm, for example an inductive proof. We already thought a lot about this, how to do such an inductive proof, but the problem which arose there was that we are not guaranteed, that we don't know which properties are guaranteed to hold in every inductive step of the algorithm, because this redundancy and coexistence property are only guaranteed to hold for the input graph. Another question is whether this axiom system or a similar one can be used to verify other algorithms for geometric graph, and if this approach can be extended, for example, to the three-dimensional space. Here's an overview about the running times of some of the tests. So you see if the number of constants in the clauses and the number of clauses is increasing, the running time is also increasing, but most of the tests were pretty fast. So that's it from my side. Now you can answer your questions.
What's the question? Nobody? So I do have a question actually.
Yeah.
Is this proof that you encode into the Börner-Schenfinkel-Ramsey fragment, is it valid for all sizes of input graphs, or is it a proof that you have to reconstruct for every size of input graph? For all sizes?
Yeah, I think it should hold for all sizes. So as you see here, we only needed sizes up to 10 vertices, but I don't see that there occurs a problem if the size increases, but we didn't check it for larger graphs.
Because then the complexity of the proof may increase, right?
Yeah, as you see, so the time these proof tasks need is increasing, and yeah, I think if you would add still some more constants, then the complexity would increase even more. And maybe there's at some point a problem that the proof won't terminate anymore and return unknown. So there was one more question.
I think Laura's one.
Yes, I just wanted to clarify that. Is it your understanding that Z3 is kind of the most natural choice to solve Börner-Schenfinkel class today, I mean, among the tools?
Yeah, we also considered taking other proof systems, which, for example, are based on hierarchical reasoning, but there were some problems on the termination. Therefore, we choose this theorem system set 3, but I didn't really check all other possible theorem proofers, so there might be maybe a better proofer, but at least with this one it worked quite well.
Okay, good. Because there's a work by Piskac and Björner on particular tuning provers for effectively propositional logic, but maybe this was implemented in fact in V3. So
yeah, I think that was implemented there.
Thank you.
Those 41 axioms that you mentioned, I don't suppose there is any chances that they have a simple structure, maybe a horn or something like that. Have you tried to see if they could be expressed in some restricted subclass of all clauses?
Yeah. So we what we did and what we already included in the appendix is that if you took out some of the axioms, then you would obtain a counterexample. So I think this would be more or less the minimal choice of axioms you need to model all these properties.
But it's not hard, probably.
No, I'm not sure that it's home, but if
I
you
see some disjunctions.
Yeah.
On the right, so.
Any other question? So I guess we can thank the speaker again and welcome the next speaker.